Alright, this is supposed to be just the steps. I just had another recording coming up to this point. Step 1, this is for method of repeating variables. Step 1, list all the variables that are involved in the problem. This step is the most difficult one, and it is, of course, vitally important that all pertinent variables be included. Otherwise, the dimensional analysis will not be correct. We're using the term variable to include any quantity, including dimensional and non-dimensional constants, which play a role in the phenomenon under investigation. All such quantities should be included in the list of variables to be considered for the dimensional analysis. The determination of the variables must be accomplished by the experimenter's knowledge of the problem, and the physical laws that govern the phenomenon. Typically, the variables will include those that are necessary to describe the geometry of the system, such as a pipe diameter, to define any fluid properties, such as fluid viscosity, and to indicate external effects that influence the system, such as a driving pressure drop per unit length. These general classes of variables are intended as broad categories that should be helpful in identifying variables. It is likely, however, that there will be variables that do not fit easily into one of these categories, and each of them needs to be carefully analyzed. Since we wish to keep the number of variables to a minimum so that we can minimize the amount of laboratory work, it is important that all variables be independent. For example, if in a certain problem, the cross-sectional area of a pipe is an important variable, either the area or the pipe diameter could be used, but not both, since they are obviously not independent. Similarly, if both fluid density ρ and specific weight gamma are important variables, we could list ρ and gamma, or ρ and g, acceleration of gravity, or gamma and g. However, it would be incorrect to use all three since gamma equals ρg. That is, ρ, gamma, and g are not independent. Note that although g would normally be constant in a given experiment, that fact is irrelevant as far as a dimensional analysis is concerned. Step 2. Express each of the variables in terms of basic dimensions. How many steps are there? Are there 12? I only see 4 so far. For the typical fluid, express each of the variables in terms of basic dimensions. For the typical fluid mechanics problem, the basic dimensions will be either m, l, or t, or force L and t. Dimensionally, these two sets are related through Newton's law F equals ma, so that F equal dot mlt minus 2, so that's ml over t squared. For example, ρ is the same as m over l cubed, or ρ is the same as f t squared over L4. Thus, either set can be used. The basic dimensions for typical variables found in fluid mechanics problems are listed in Table 1.1 in Chapter 1. Determine the required number of pi terms. This can be accomplished by means of this is Step 3. Step 3 is determine the number of pi terms. This can be accomplished by means of the Buckingham Pi Theorem, which indicates that the number of pi terms is equal to k minus r, where k is the number of variables in the problem, which is determined from Step 1, and r is the number of reference dimensions required to describe these variables, which is determined from Step 2. The reference dimensions usually correspond to basic dimensions and can be determined by an inspection of the dimensions of the variables obtained in Step 2. As previously noted, there may be occasions, usually rare, in which the basic dimensions appear in combinations. So I just said that because usually rare, it just means it's frequently rare, which the basic dimensions appear in combinations so that the number of reference dimensions is less than the number of basic dimensions. This possibility is illustrated in 7.2. So what was that? Previously noted, it's the basic dimensions, reference dimensions less than the number of basic dimensions. Interesting. Hopefully I'll know what that means soon. Step 4. Select a number of repeating variables where the number required is equal to the number of reference dimensions. I'm going to repeat that. Step 4. Select a number of repeating variables where the number required is equal to the number of reference dimensions. Essentially, what we're doing here is selecting from the original list of variables, several of which can be combined with each of the remaining variables to form a pi term. All of the required reference dimensions must be included within the group of repeating variables, and each repeating variable must be dimensionally independent of the others. That is to say, the dimensions of one repeating variable cannot be reproduced by some combination of products of powers of the remaining repeating variables. This means that the repeating variables cannot themselves be combined to form a dimensionless product. For any given problem, we usually are interested in determining how one particular variable is influenced by the other variables. We would consider this variable to be the dependent one, and we would want this to appear only in one pi term. Thus, do not choose the dependent variable as one of the repeating variables, since the repeating variable will generally appear in more than one pi term. Step 5. For a pi term, form a pi term by multiplying one of the non-repeating variables by the product of the repeating variables, each raised to an exponent that will make the combination dimensionless. Essentially, each pi term will be of the form u sub I, u1 to the a I, u sub 2 to the bi, u sub 3 to the ci, where u sub I is one of the non-repeating variables, u1, u2, and u3 are the repeating variables, and the exponents a sub I, b sub I, and c sub I are determined so that the combination is dimensionless. Step 6, repeat step 5. So tempted to repeat step 5 right now. Repeat step 5 for each of the remaining non-repeating variables. And again, just the bold part of step 5. Form a pi term by multiplying one of the non-repeating variables by the product of the repeating variables, each raised to an exponent that will make the combination dimensionless. So step 6 again, repeat step 5 for each of the remaining non-repeating variables. Okay, I think, actually, so repeat step 5 for each of the pi terms. The resulting set of your pi terms will correspond to the required number obtained from step 3. If not, check your work. You have indeed made a mistake. Step 7. Check all the resulting pi terms to make sure they are dimensionless. It is easy to make a mistake in forming the pi terms. However, this can be checked by simply substituting the dimensions of the variables into the pi terms to confirm that they are dimensionless. One good way to do this is to express the variables in terms of ml and t if the basic dimension is fl and t, vice versa. Check to make sure the pi terms are dimensionless. Step 8. Express the final form as a relationship among the pi terms. Oh, nice. All right. See, it doesn't go on forever. Express the final form as a relationship among the pi terms and think about what it means. Typically, the final form can be written as pi 1 equals phi of pi 2, pi 3, and all the other pi's, where pi 1 would contain the dependent variable in the numerator. Okay, so pi 1 would contain the dependent variable in the numerator. It should be emphasized that if you start out with the correct number, the correct list of variables, and the other steps were completed correctly, then the relationship in terms of the pi terms can be used to describe the problem. You need to work on the pi terms, not the individual variables. However, you need to work, that sentence. You need to only work with the pi terms, not with the individual variables. However, it should be clearly noted that this is as far as we can go with the dimensional analysis. That is, the actual functional relationship among pi terms must be determined by experiment. To illustrate these various steps, we will again consider the problem discussed earlier in this chapter, which was concerned with the steady flow of an incompressible Newtonian fluid through a long, smooth-walled, horizontal, circular pipe. We are interested in the pressure drop per unit length, delta P sub L, along the pipe as illustrated by the figure in the margin. First, step 1, we must list all of the pertinent variables that are involved based on the experimenter's knowledge of the problem. In this problem, we assume that delta P sub L is a function of diameter, density, viscosity, and velocity, where d is the diameter of the pipe, rho and u are fluid density and viscosity, and v is the mean velocity. Step 2, we express all the variables in terms of basic dimensions using FL and T. D is L, rho is Ft squared over L4, mu is Ft over L squared, and V is L over T. We could also use the ML and T at basic dimensions as desired. Okay, it's going to talk about the FLT again. Don't mix those things. We can now apply the pi theorem to determine that the required number of pi terms, step 3. An inspection of the dimensions of the variables from step 2 reveals that all 3 basic dimensions are required to describe the variables. Since there are 5, k equals 5, variables, do not forget to count the dependent variable delta p sub l, which I did do previously, and 3 required reference dimensions r equals 3. Then according to pi theorem, 5 minus 3 equals 2. It doesn't say that. Oh, or 2 pi terms. It does say that with letters. The repeating variables to be used to form the pi term, step 4, need to be selected from the list D rho mu and v. Mu. Remember, we do not want to use the dependent variable as one of the repeating variables. Since 3 reference dimensions are required, we will need to select 3 repeating variables. Generally, we would try to select as repeating variables those that are simplest dimensionally. For example, if one of the variables has the dimension of a length, choose it as one of the repeating variables. In this example, we will use d, v, and rho as repeating variables. Note that these are dimensionally independent. Since d has a length, v involves length and time, and rho involves force, length, and time. This means that we cannot form a dimensionless product from this set. We are now ready to form the 2 pi terms. Step 5. Typically, we would start with the dependent variable and combine it with the repeating variables to form the first pi term. That is, pi 1 equals delta p sub l, d to the a, v to the b, and rho to the c. Since this combination is to be dimensionless, it follows that f over l cubed times l to the a times l over t to the b times ft squared over l4 to the c equals, dimensionally equals, f to the 0, l to the 0, t to the 0, which is 1. The exponents a, b, and c must be determined so that the resulting exponent for each of the basic dimensions f, l, and t must be 0 so that the resulting combination is dimensionless. Thus, we can write for f and for l and for t, we find out the exponents to make them 0. The solution of this system of algebraic equations gives the desired values for a, b, and c, and it follows that a equals 1, b is negative 2, and c is negative 1. Therefore, pi 1 equals delta p sub l, that's the thing, so that's the first one, that's to the 1, times d over rho v squared. The process is now repeated for the remaining non-repeated variables, step 6. I need a sip, sorry. Alright. Process is now repeated for the remaining non-repeating variables, step 6. In this example, there is only one additional variable, mu, so that pi 2 equals mu d to the a, v to the b, rho to the c, or ft over l squared times l to the a, l over t to the b, ft squared over l4 to the c. It's dimensionally equivalent to f to the 0, l to the 0, t to the 0, which is 1. We want to make all those exponents 0. And starting with the simplest one, so there's only, let's see, is that the simplest one? 1 plus c. Anyways, and for 1 plus c, 0 for f. And L, and then we get the A, B, and C. Can I take a second? How does it equal 1 plus c for f? We've got f to the c. There's 1f. So we just have L over T, and ft squared over L. So you want to balance out that first L, which doesn't have an exponent, with the the first F, which doesn't have an exponent, with the F on the right hand in the C parentheses, and so F to the 1. You just need the negative 1, so that makes sense. All right, and so solving these equations simultaneously, it follows that A equals negative 1b, negative 1c, negative 1, so that pi 2 equals mu over dv rho. Note that we end up with the correct number of pi terms as determined from step 3. At this point, stop and check to make sure the pi terms are actually dimensionless. Step 7. Just do it. Shouldn't take too long, right? We will check using the FLT and MLT dimensions. Thus, pi 1 equals delta pi sub L d over rho v squared. They throw all the things in there and say, hey, we didn't make a mistake because we're publishing a book here and we got our shit right. All right, so finally, step 8. We can express the result of the dimensional analysis as delta p sub L d over rho v squared equals phi super tilde times mu over dv rho. And we got a mu over dv rho there, right? Can you see what I'm doing? Yeah. And then delta p sub L d over rho v squared. Delta p sub L d over rho v squared. So pi 1 equals phi of pi 2. Right? As a function of pi 2. This result indicates that this problem can be studied in terms of these two pi terms, rather than the original 5 variables we started with. The 8 steps carried out to obtain this result are summarized by the figure in the margin, over there to the left. Dimensional analysis will not provide the form of the function phi. This can only be obtained from suitable set of experiments. If desired, the pi terms can be rearranged. That is, the reciprocal of mu over dv rho could be used, and of course the order in which we write the variables can be changed. Thus, for example, pi 2 could be expressed as pi 2 equals rho vd over mu, and the relationship between pi 1 and pi 2 as d delta p sub L over rho v squared equals phi of rho vd over mu. As shown by the figure in the margin, this is the form we previously used in our initial discussion of the problem in equation 7.2. The dimensionless product rho vd over mu is a very famous one in fluid mechanics. It's the Reynolds number. This number has been briefly alluded to in chapters 1 and 6 and will be further discussed in 7.6. To summarize, the steps to be followed in performing a dimensional analysis using method of repeating variables are as follows. Step 1. List all variables that are not involved in problem. Step 2. Express variables in terms of basic dimensions. Step 3. Determine the required number of pi terms. Step 4. Select number of repeating variables where number required is equal to number of reference dimensions, usually same as number of basic dimensions. Step 5. Form a pi term by multiplying one of non-repeating variables by product of repeating variables, each raised to exponent that will make combination dimensionless. Step 6. Repeat step 5 for each remaining non-repeating variables. Step 7. Check all resulting pi terms to make sure are dimensionless and independent. Step 8. Express final form as relationship among pi terms and think about what it means and what you're doing with your life. Some additional comments. Determination of reference dimensions. Another example. Uniqueness of pi terms. A little reflection on the process used to determine pi terms by the method of repeating variables reveals that the specific pi terms obtained depend on somewhat arbitrary selection of repeating variables. For example, in the problem of studying the pressure drop in a pipe, we selected dv and rho as repeating variables. This led to the formulation of the problems in terms of pi terms as del sub L d over rho v squared equals phi of rho v d over mu. What if we had selected dv and mu as repeating variables? A quick check will reveal that the pi terms involved delta p sub L becomes delta p sub L d squared over v mu. And the second pi term remains the same. Thus, we can express the final result as delta p sub L d squared over v mu equals phi 1 times rho vd over mu. Both results are correct and both would lead to the same final equation for the delta p sub L. However, note that the function phi and phi 1 in equation 7.5 and 7.6 will be different because of the different pi terms are different for the two relationships. As shown by the figure in the margin, the resulting graph of dimensionless data will be different for the two formulations. However, when extracting the physical variable delta p sub L from the two results, the values will be the same. We can conclude from this illustration that there is not a unique set of pi terms which arises from dimensional analysis. However, the required number of pi terms is fixed, and once a correct set is determined, all other possible sets can be developed from this set by combinations of products of powers of the original set. Thus, if we have a problem involving, say, 3 pi terms, pi 1 equals phi of pi 2 and pi 3, we could always form a new set from this one by combining the pi terms. For example, we could form a new pi term, pi prime 2, by letting pi prime 2 equal pi a prime, pi a 2, pi b 3. Where a and b, these are exponents, are arbitrary exponents. And the relationship could be expressed as, and I have an incoming call, so excuse me.